All right, so we got to finish this section 4.2. We got to finish up. We talked about this Riemann sum thing where we were estimating area under a curve and playing with all these rectangles and stuff. Well, now these Riemann sums translated into this terrible limit definition down here on the bottom. So what I'd like to do in this video is I'd like to put it in practice. What's it look like when we do? So here's a function. Find the area underneath this thing on the interval between 1 and 3. Interval between 1 and 3. So I'm supposed to come up with this thing using one rectangle, estimating it using one rectangle, estimating it using two rectangles, and then ultimately estimating it using the limit definition. And when you do it with the limit definition, it's going to give you an exact area. We're going to figure out what that value is exactly. So I've already graphed 2x plus 3. And let's say I wanted to use, we're supposed to be on the interval between 1 and 3. So 1 and 3, so here's x equals 1, and here's x equals 3. So that's the box I'm supposed to be staying within. And what I'm going to do, if I wanted to use one rectangle, so the question is, do you want the left side of that rectangle to hit your graph, or do you want the right side of that rectangle to hit your graph? So let's say, in red, I'm going to stay with my pattern, I'm going to make the left side of my rectangle hit the graph. So I'm going to start at x equals 1, and I'm going to draw myself this rectangle. So there's my one rectangle. Is that going to do a good job estimating the area under the curve? No, it's going to be way too small. But if I said do that, did one rectangle. So what's my change in x? What's my width? 3 minus 1 divided by one rectangle says that rectangle is 2 units wide. How tall is that rectangle? We're going to use the left endpoint. Well, that left endpoint is 1. So what is f of 1? In this case, well, 2 times 1 is 2, plus 3 is 5. If I want this area, I'm going to take the f of the left endpoint and multiply it by 2, and I'm going to get 10. If I wanted to use the right endpoint, well, now I could make it look that way. So the blue one, that's going to be way too high. It's not going to be any good. Change in x is going to be the same thing. Change in x doesn't matter. It just matters how many rectangles you're using. It's not going to change. It's still going to be 2. But this time I'm going to do f of the right endpoint. Well, what's my right endpoint of that rectangle? It's 3. What's f of 3? 2 times 3 is 6, plus 3 is 9. This area, 9 times 2, or 18. Are either of these accurate? No. In fact, you've probably already figured out that if you average those two together, you'd have it exactly. And because we have a linear function, that will work. When we have any other kind of function, which is most of the time, it's not going to work so well. So there's one rectangle. What's it look like when we do two rectangles? Well, two rectangles, now things change a little bit. Well, how wide is each rectangle going to be? Well, if I'm going from 1 to 3, here's x equals 1, and here's x equals 3, then each rectangle is going to be 1 unit wide. The interval, 3 minus 1, starts at 1, goes to 3, divided by, this time I'm using two rectangles. So if I go to do that, so then each rectangle is going to be 1 unit wide. So I'm going to put in, let's start with red. If I'm going to put in two rectangles, red, first rectangle is going to be that wide. It's going to be f of 1 unit tall. Second rectangle is going to be f of 2 units tall. So red, first rectangle is going to be 1 unit wide by f of 1 unit tall, plus second rectangle 1 unit wide by f of 2 units tall. What's f of 1? We already went through it. 2 times 1 is 2, plus 3 is 5, plus f of 2. 2 times 2 is 4, plus 3 is 7. What's my area under the curve estimate? It's 12. How would that be different if I did the blue? Well, the blue, first rectangle, f of 2 units tall. Second rectangle, f of 3 units tall. So the blue one's going to overestimate, but my area, first rectangle 1 unit wide by f of 2 units tall, plus second rectangle 1 unit wide by f of 3 units tall. What's f of 2? We already said that's 7. What's f of 3? 3 times 2 is 6, plus 3 is 9. This area under the curve's estimate would be 16. Which one's right? Doesn't matter. It says estimate. It doesn't say which endpoints to use. Mr. Perkins, why didn't you use all that sigma business? Why didn't you use all that crazy stuff? Well, because they told me I had a nice number of rectangles that I knew, and it's much faster in Part B to estimate each rectangle, to figure out each rectangle's area and add them together than it is to bring in things like our friend sigma. I only bring in things like our friend sigma when it tells me to. How does it tell me to? Use the limit definition. Oh boy. Okay, let's start by writing down what the limit definition is. Limit definition. We said sigma I equals 1 to n of f of, and we're always going to use the right endpoint when we do limit definition, times change in x, and ultimately we're going to take the limit as n approaches infinity of all of this. And when we get done with this, this is going to give us the exact area under the curve. And some of you might be saying, oh, well, you know, I could probably use geometry to figure it out now. That's good. That'll be a great way to check to make sure what we did is right. So here's what we're going to do. The first thing I need to know, we're going to break this down piece by piece. The first thing I'm going to figure out is the easiest thing. I want to know what is change in x. That's the very first thing we're going to figure out. So let's figure out what change in x is. Well, my interval is still going from 1 to 3. And I'm putting in I don't know how many rectangles. So you figure out change in x the same way we did above. 3 minus 1 divided by the number of rectangles. How many this time? Last time it was 2. This time we don't know. 2 over n. The second thing we're going to do is we're going to come up with what the right endpoint is. Not f of the right endpoint, but what the right endpoint is. So the right endpoint of each rectangle goes like this. The right endpoint is always going to be, and I wrote it down in the last video, a plus I times change in x. A plus I times change in x. What's a? A is always the left bound. What's the left bound in this problem? It's going to be 1. What's change in x? Wait a minute. Oh, we've already figured that out too. So we're going to now figure out what is the right endpoint. The right endpoint, a plus I times change in x. A, in this case, is 1 plus I times what's change in x? Change in x we just figured out is 2 over n. So what do I have for my right endpoint? 1 plus 2i over n. Step 3. Now let's do f of that right endpoint. F of that right endpoint. Okay, f of that right endpoint. Well, let's see. What's our f in this case? F of x was given in this problem to be 2x plus 3. So f of the right endpoint would say everywhere you see an x, plug in the right endpoint. What's the right endpoint? We just found it above. It's 1 plus 2i over n. So we're going to want 2 times something plus 3. What's the something? 1 plus 2i over n. Well, let's clean that up a little bit. Distribute the 2. 2 plus 4i over n plus 3. How about 4i over n plus 5? That's your f of the right endpoint. So what we have right now is we have everything that needs to go inside the sigma. What's the fourth step? The fourth step is now let's take care of sigma. So step 4, our friend sigma. Sigma. Okay, so sigma I equals 1 to n of f of the right endpoint. Oh, what's f of the right endpoint? Oh, wait a minute. F of the right times change in x. Do we have all those pieces? Yes, we do. The right endpoint is 4i over n plus 5. times change in x, which is 2 over n. And we're going to do sigma of all of this. Well, is that a hard sigma problem? We've been practicing that a little bit. What's the purple thing? Wait a minute. We could distribute it. In fact, I'm going to do this. I'm going to do it without writing all the sigma stuff down. If I do it without writing all the sigma stuff down, and if I just take what's inside the orange, then this first term would be, let's see, 2 over n times 4 over n times I. How about 8i over n squared plus 5 times 2 over n would be 10 over n. And that's what's inside that quantity right now that we're supposed to be doing sigma of. Well, 2 different terms means 2 different sigmas. Sigma I equals 1 to n of, wait a minute, 8 over n squared. That's not going to have anything to do with the counter. So let's put the 8 over n squared on the outside. Of I. Ooh, we have shortcuts for that. Plus, let's put, wait a minute, 10 over n, that's not going to have anything to do with I. That's just going to be a, you could pull it out if you wanted to. I equals, sorry, 10 over n, that's just a constant. So if I wanted to clean this up, let's see here. So I've got 8 over n squared times, what's the shortcut for this little beauty right here? I think it's n times n plus 1 divided by 2. Plus, what's the shortcut for this one? Isn't it n times 10 over n? So if we start cleaning all of this stuff up, we're really in business. We're in great shape right here. Because this is a 10, and this is really 8n squared plus 8 over 2n squared. And I'm going to stop right there. Okay, so I've taken care of step 4. Step 4 is the one that's the most cumbersome right here, because you're going to go through your shortcuts and stuff and try to work your way through them. Last but not least, last but definitely not least, is your limit. We're going to take care of the limit. So now I'm going to do the limit as n approaches infinity of 8n squared plus 8 over 2n squared plus 10. So if I go to do that, what's that limit going to be? Well, we could go through our normal process. What's the limit of any limit of a constant? This is just a 10. But this other one, I'm looking at it and I see that the degree of the top is 2 and the degree of the bottom is 2. If they're the same, the only thing that matters is the coefficients in front of that thing. When we've done those limits as n approaches infinity, this limit is really 8 over 2 or 4. Clean all this up. What's this limit going to be? This limit is going to be 14. And that 14, what the heck does it mean after all of that business? That 14 is the exact area under the curve of that function in between 1 and 3. Heavy math today.